Now, one really important molecule in nature is isoprene. We see isoprene all over the place. Some of you are aware of a class of molecules called terpenes. Terpenes are things like limonene, or, which gives like a citrusy smell to citrus fruits. Or in this case here, I'm showing a reaction of how isoprene units can be linked together to form a polymer called rubber. So we're all familiar with rubber. So anyway, these kinds of reactions usually occur from kind of linking using the pi system. So here are three kinds of reactions that take advantage of pi bonds to form sigma bonds. So here, cycloaddition means that you're adding two molecules together to make a cyclic compound. Here we have electrocyclic reaction, so just within one compound you can get a ring forming. So notice this is really different from what we've done before. These are pi bonds forming sigma bonds. Okay, and then there's something called sigmatropic rearrangement. You can get a different isomer here. So the ones we're going to focus on right now is the cycloaddition reaction. The cycloaddition reaction we want to focus on in particular is something we call a 4+2 cycloaddition, and this is named after two scientists, Diels and Alder. So we call it the Diels-Alder reaction. It's what we call a named reaction. It's named after people or someone. Now the 4+2 is referring to the pi electrons. So I have a molecule with 4 pi bonds being added to a molecule with 2 pi bonds. Okay? In other words, 4 pi bonds meaning 4 pi electrons meaning 2 pi bonds, or 2 pi electrons meaning 1 pi bond. Okay? And so the way that this works is follow the arrows and you will be able to see all. Okay? You'll be able to figure it out. Okay, so what happens is the diene is the molecule with the 2 pi bonds. Diene. And I have a funny mug, by the way. Maybe I'll show you right now just on the internet. All right, so you guys gotta love Pinterest, right? So here's a little drawing somebody made before organic chemistry exam, after organic chemistry exam, and notice the 2 pi bonds here is I'm dying. I'm dying. So anyway, it's really cheesy, but I love it. I have a mug that says that. So diene. Okay, and the molecule it reacts with loves dienes, and it's what we call the dienophile because it reacts with dienes. And so if we follow the arrows here, we make a new sigma bond with a pi bond, then that causes this to shift down here and make a new sigma bond down here, and then that causes this to shift over here and make a pi bond over here. So we're making 2 sigma bonds and a pi bond from 3 pi bonds. And notice the new bonds right here and right here are highlighted. So these new bonds right here are highlighted right here. All right? So I think this is a really fun reaction with the arrows. So now let's think about the thermodynamics of this reaction. We have 2 molecules turning into 1. So 2 molecules turning into 1, what does that do for entropy? Does it increase it or decrease it? Well, we would say that the entropy is decreasing because we're lessening the disorder, right? But if we decrease delta S, which means that delta S is negative, then the negative sign that's already in the equation is going to turn that whole term into a positive. Negative and negative make a positive. And we know that delta G is spontaneous if it's negative, right? So we don't want this term to be positive. We want the overall term to be negative, to be more negative delta G or more product driven. So how do we make it more spontaneous then? How do we make it more product driven? Well, what do we need to do to the T to make this delta G more product driven? Do we need to decrease the T or increase the T? What does that do to this term? Well, if I have a positive term here and I want the overall to be negative, I need to minimize the effect of that positive. So I need to decrease the T. So it turns out for the Diels-Alder reaction, we want high enough temperature to overcome the activation energy, but we don't want it to be too high because that will then make the product more reactant favored. So it turns out you could do the reverse reaction at a higher temperature. And that's called a retro-Diels-Alder reaction if you go in reverse. So notice the examples we have here from Klein. If you have a high temperature like 200 degrees C or higher, you're going to have only 20% yields for this particular reaction because you have such a high temperature. You're going to have most of the reaction going the other way. Now, another way that we can increase the yield of these reactions is to add an electron withdrawing group. An electron withdrawing group is a molecule that has an inductive effect, meaning let's take a look at the carbonyl group, for example. We have a dipole like this. So that tells me that there's induction, meaning the electrons are going to move toward the O because of its electronegativity. And that helps to make this carbon here more electrophilic or more positive. That means that this is going to be much happier to attack there, causing this reaction to occur faster. Other electron withdrawing groups are ketones. This one is an aldehyde, esters, carboxylic acids, or even cyanide. If you draw this out, you have this, and you can see the dipole this way, which makes this carbon more electropositive. Adding electron withdrawing groups is going to help make your rate faster or rate higher. And then note about the stereochemistry. This one's an easy one to remember. Notice that we have the same side, and these are going to be same side. Okay, so cis turns into cis. A trans alkene will have a trans dihalide here in this case, or just the groups that are on there are going to stay trans. So now let's do some of these Diels-Alder practice problems. Again, I like to use mechanism to try to figure this out. I have my diene here, and I have my dienophile here. Now, this one's a little confusing because I have 2 pi bonds. This is an alkene, and I haven't seen alkenes in this reaction yet, right? So let's highlight the pi bonds that are involved, and I'm going to use my arrows, and I'm going to attack here. I'm going to make a sigma bond here. I'm going to make a sigma bond there. So I'm going to make my sigma bond between these two. I'm going to make a sigma bond between these 2 carbons, and I'm going to move my pi bond to make a pi bond there. So this is still, I'm treating this alkyne, I'm only using one of the pi bonds because that's all I need, right? So that means I'm going to have a 6-membered ring like that. Now this is linear, so I'm going to have not cis or trans. I guess I could have something like that because it's actually planar here because I have my pi bond still there. Okay, and then I've got this pi bond moved over to here, so that ends up right here. So this is my product. Let's try one down here. So now you see the cyanide groups are trans. So let's try this here. I'm going to attack this to here, make a pi bond there. A sigma bond, I mean. Here I'm going to make a sigma bond here, and I'm going to move that there. So I'm going to make my 6-membered ring, and then I'm going to have my cyanide groups be trans to each other because they were trans in the dienophile. All right, and this reaction should be pretty fast, as well as this one, because of the electron withdrawing groups on the dienophile. Now, can you guys see why this might be no reaction? We haven't talked about it yet, but see if you can figure it out. I'll give you a hint. There's something wrong with the diene. Dienophile looks great. So I don't know if you caught it, but we talked about S-cis versus S-trans. So when we have a diene, notice that these dienes are in the S-cis configuration. See how they are cis right here? In this case, we have an S-trans, but it's fixed in a ring, so it cannot rotate to an S-cis. The reason why we want S-cis is because it's all ready to go to make a 6-membered ring. But here, we don't have that configuration. So because this is STrans, it's in the wrong configuration to make a 6-membered ring. So it's too slow to form. It's just out. It's twisted out. You can't bring them back together to make a 6-membered ring. So another thing to think about with Diels-Alder is making a bridged compound. If our diene happens to be cyclic, then we can fold this up into a bridged carbon like that, and then we can have the reaction occur sort of like this. Here's our diene, so it can form here, of course, and then this can form here, and this can go in here. But what about this bridge right here? Okay, it sort of gets in the way, right? Think about that bridge as folding up into this. All right, so here's my new sigma bonds. Let me highlight them. So right here and right here. And then right here is right here. All right, so these are my new sigma bonds. This is my new pi bond from this guy over here. Okay, and what happens here is I have a trans dihalide, and so it stays trans here. So it turns out there's a lot of stereochemistry in this part right here. If it's trans, one is down, one is up. Now notice this is in a cyclic ring. This is called a bicyclic compound because there's one ring right here, and then there's another ring right here. And where that other ring is formed makes an axial position and an equatorial position. So notice when this is trans, I'm going to have one axial and one equatorial because this is down and this is up. So they're opposite side. Now if these were on the same side, notice I'm going to have either two of them axial or two of them equatorial to be on the same side. Now they're not the same thing because unlike a chair, these do not flip. So I'm going to end up with either what's called the endo form, which is the axial down, or the EXO, which is the equatorial up. And then one last note, if you could have these two groups, you could have this molecule flipped, and then you could have the equatorial here and the axial here. So that's why it says plus enantiomer. But as long as they're trans, you can have either version. So looking at using the terms endo and exo, which product of this example puts the groups axial? So the axial ones are what we're calling endo. Equatorial is the exo. And which one seems more stable to you? Thinking back to cyclohexane chairs, do we say axial or equatorial tended to be more stable? Well, I think you guys remember equatorial means you're pointed away from the ring. Like these guys are not as repulsive as these guys are in terms of hydrogens being, nearby. They tend to have more electron repulsion because they're closer inside the ring. That's why we call it endo, is because it's inside the ring system right here. Whereas exo is a little bit more outside. Okay, so I think thinking back to cyclohexane, the exo version is what we remember as being more stable. So that's true, it is thermodynamically more stable, but endo is usually the kinetically favored product. So that is, it tends to form faster. And it turns out that it has a lower activation energy for these Diels-Alder reactions, and the belief is that it's because of these favorable interactions between the electron withdrawing substituents and the pi system, that there's a kind of favorable interaction or overlap. And so you can see down here in this example, we're adding these two groups here. The aldehyde groups have these pi systems here, and we're also using the pi system to create the cycloaddition reaction. So if those have alignment, you could see that they have better interaction when these groups are closer, as in the endo form. So that's why endo tends to be favored in Diels-Alder reactions. So let's do some practice where we consider first what is the Diels-Alder product, and then think about the stereochemistry. Do we have exo or endo? And let's practice drawing them. So all of these examples are with the bridged carbon. So once we do the Diels-Alder reaction, so I'm going to attack here, attack there, attack there. Okay, so I'm going to end up with this bridged carbon right there, and then I'm going to have the rest of this ring like this. And you guys will get used to drawing these with a little bit of practice. Then with the other molecule, I'm going to have these two carbons are right here, and then I'm going to have the cyanide groups. Now they're cis to each other, so either they're both going to be exo, like this, or they're both going to be endo. And I think you know from our discussion just now that the endo is going to be the favored form because of the pi system here in the cyanide groups, which I guess it would help to draw that out, right? So see all these pi bonds in the cyanide groups are going to have a favorable overlap with the pi bond and the pi system that created the cycloaddition reaction. And then let's not forget our pi bond from this right here. So this is my exo, this is my endo, and this will be my major product. All right, so go ahead and practice these as well. I think here you'll see you'll have one equatorial, one axial because it's trans, and then here you should have an endo product as well. All right, so here's what I got. You have the trans cyano groups here, and then don't forget the O there. And then here you have the endo for that aldehyde group, CHO. Now we see something with modifying the diene. Okay, so we talked about how great it is to have electron withdrawing group. Again, CHO is a C double bond OH. It's an aldehyde. Is a CHO group. Okay, so know that for biology and biochemistry. It's really important. So this is electron withdrawing, so that helps to make this more positive here. Now with the with an electron donating group, this is a donating group. The reason why is because the O has lone pairs, so that helps to donate in. So that makes these carbons more negative and more nucleophilic. Okay, so if this is more negative here, then we can think of it as down here. Okay, so that picture leads to this idea that if we donate electrons inward, we have a negative pool, negative charge right here. Now, if we think about this, we also have resonance where we move these electrons up like that. So that puts more positive charge on this end carbon, and that's why it's flipped here, because there's more positive charge here. So in this case, it turns out that when we match negative to positive, we have a Diels-Alder reaction this way, and that puts my methoxy group up here, and that puts my aldehyde group down here, rather than the other way around, like that. Okay? So you need to consider resonance and electronic factors as well in the Diels-Alder, particularly when you have an option of flipping the molecule, reacting it, or flipping it this way and reacting them together. So with that idea in mind, let's try some of these. And what I recommend is that we draw out the aldehyde group. So instead of CHO, I want to think about it as C double bond OH, and I want to think about the resonance going like this, because this is an enal, right? An ene and an aldehyde. So that puts a positive charge here on this carbon. And let me highlight that positive charge right here. And then where's my negative charge on here going to be? Can you guys predict where that's going to be? Remember, my O is electron donating, not withdrawing, so it's going to go down here. Do you see resonance? So I actually see it like this. So I see negative charge pooling there, right here. So positive here, negative here. So these two are going to want to get together. All right, so that means I'm going to have my Diels-Alder reaction in red here, here, and here. So actually, I like the way they're aligned in this case. So I'm going to put that together, and I'm going to end up with this reaction here. Okay. So notice for Diels-Alder, I always end up with a pi bond, and I end up with two new sigma bonds right here. And here's my pi bond that moved. And then for these guys here, I'm not actually pushing the electrons, I'm just doing that to show where the positive and negative charges are more concentrated. But I'm going to keep the methoxy and the aldehyde as is. I'm just using this as a tool in thinking about the electron distribution. Okay, so go ahead and try these on your own, and let's check back on the answer. Alright guys, so for part B, I did my little analysis here. It turns out this is conjugated, but this is not. So when these get donated in, I get negative charge here, and then these can move up, and so this is positive. So I want to link these two together, so I just kept it as is. But for part C, notice the positive is down here and the negative's up here. So I flipped this, so like that. And I also expanded CO2 ET means C double bond O, O ET, it's an ester. So it helps to figure out what are they talking about, okay? And then here, the negative charge here with the positive charge here, but I moved it up to here. So now I do the Diels-Alder arrows and cycloaddition, and then I'm going to write out the product. So remember, this is my bridged carbon right here. Okay, and I have my OET out here. And then I'm going to have, now this is a triple bond, so I have one pi bond that reacted, one pi bond remains. And then I'm going to have this C double bond O, OET, but I have this planar, this is sp2, so it's not going to be endo or exo. And then maybe just for brevity, I'm going to convert it back to the letters CO2ET. And then don't forget this last one right here, that pi bond. Okay, so let's think about back to molecular orbital theory and what that all had to do with this. So if we have, let's say, the butadiene, 1,3-butadiene, so here's butadiene, and here's my dienophile, which is ethylene. So the idea of the HOMO and LUMO comes in right now. So basically the idea is when we look at the molecular orbitals of butadiene, so back a few videos ago, we talked about the HOMO of butadiene and the LUMO of butadiene. And you can also do the same for ethylene. So try to remember this, we'll come back to it. And for ethylene, there's just two carbons, right? CH2, CH2. And so for ethylene, it's going to be either two orbitals like this that are aligned, that's the lower energy one, and then with one node, you're going to have the opposite, right? And so this is going to be bonding and antibonding. And for ethylene, we only have two pi bonds, so 2 pi electrons, I mean. So we have the HOMO down here and the LUMO right here. So now we're going to consider the molecular HOMO and LUMO, or molecular orbitals, for the butadiene and the HOMO and LUMO for the ethylene. So here are the different combinations. You could either have the HOMO of butadiene, which looks like this. If you go back to that diagram, we see 2 in phase and 2, and then a node, and then the 2 in phase again, like that, but the opposite. Let's go back and verify that. So here's the HOMO of butadiene. We have 2 in phase that way, and then a node, and then 2 in phase again. So let's say we happen to take the HOMO of the diene and the LUMO of the dienophile. and the dienophile is ethylene. So the LUMO is going to be the lowest unoccupied molecular orbital, and that's the one where they're out of phase, okay, so with one node. So over here, that's what they have. Well, it turns out when you match the HOMO of one and the LUMO of the other, do you guys see how this is in phase, same color, and this is in phase, same color? So it turns out that there is bonding interaction there, and that's why we have a reaction. Okay, so all of this is based on molecular orbital symmetry, which is really cool. Now let's see what happens. What if we had the LUMO of butadiene and the HOMO of ethylene? Or let's see why ethylene, HOMO of ethylene, and LUMO of ethylene don't react together. So if you had two ethylene reactions, or two ethylene molecules, they actually don't react in this kind of cycloaddition. Isn't that weird? Like you would think, here's one ethylene, here's two ethylene, and why can't they just do that? Well, it turns out that this idea of the frontier molecular orbitals, HOMO of one, the LUMO of the other, they don't match up. We're not going to see a reaction. And that's what happens here. Let's take the HOMO of ethylene, where we have in phase, and the LUMO of another ethylene, which is out of phase. And notice here, they're out of phase. So they're not predicted to react together. So this is what we call forbidden. Okay, so we don't expect a reaction in that case. Now back to what I was about to do. Would we get a reaction if we had the LUMO of butadiene and the HOMO of ethylene? Maybe I'll leave that up to you to try to go back and see would those result in a reaction or not. Now, even though the two ethylenes here didn't react because they're out of phase, it's possible that with some light, energy, photons, heat, you can get excitation, right? So the electrons can jump up to a higher state. So now this is an example of what we call a photochemical reaction. So you have photons that excite the molecule. It's possible you can change the HOMO and LUMO because it just results, HOMO and LUMO is determined by where the electrons are, right? So if we excite the electrons, then our LUMO becomes our HOMO now. Okay, so this results in changes in reactivity. So here's an example. We take the HOMO of the excited state of ethylene. Well, in the ground state, it was in phase, but if we excite the electron, that means it can jump to a higher state. So remember before, this was our HOMO because that was the highest occupied molecular orbital. Well, when we excite the electron, then we change that. This becomes our HOMO now, right? So out of phase, right here, out of phase, okay? But in the ground state, we had a LUMO was right here. So before the excitation, our LUMO was this ground state, was the out of phase molecular orbitals. And now you can see that the HOMO of one, and when it's excited, matches for positive bonding interactions with the LUMO of a ground state ethylene, that is an ethylene that's not excited. So that means that you can get reaction. So probably for this part, I would like you to be able to draw really simple molecular orbital diagrams for simple pi systems, 2 carbons, 4 carbons, and I'd like you to be able to identify the HOMO and LUMO and let me know with various combinations would you expect a reaction to occur or not, and what happens when I excite the electron, who is now the HOMO and the LUMO then. And then just for out of your own interest, there are molecules with lots of conjugation, like lycopene. You've heard of this molecule in tomato sauce, for example. And you've also heard of beta-carotene. So look at all the conjugation here. And this molecule here, which is in sunscreen. And the reason why this molecule works so well as a sunscreen is because of the conjugation here. Turns out that molecules that are highly conjugated not only are often colored compounds because of their interaction with visible wavelengths of light, but also because they can absorb in the ultraviolet range And of course, that's what sunscreens help us do, is protect our skin by absorbing harmful UV rays. And of course, that's what sunscreens do, is absorb harmful UV rays, which it handles through its conjugated system so that it doesn't get to our skin and DNA, which can then cause cancer.